Pretty weird. I just saw him in the hall. Oh, here he is. Hey. How you doing? You have a good break?
Yeah.
It's good.
How about you?
Pretty good. I didn't do anything. I planned to take a trip, but I didn't do it. That's not it. It's kind of interesting. That's it. Let's see. Did you go anywhere or anything? No. Anybody go anyplace? No. To Tennessee? To where? Oh, Nashville. That's pretty good. That's better than anyone else. You by far beat us. Let's see. So I need the new. Let's see. Dynamics. New routes. That's what I need. All right. So I want to just go like kind of start over in the slide set and then go through the dynamic stuff. It's a little bit hodgepodge here. If anyone has anyone looked at that homework yet too? Like probably I could probably go through that too if you wanted. Anyway, if we need it. But, anyway, let me just do this now first. This is kind of the same thing anyway. This homework. Let's see. So there's this. Your mic's on.
12th open and
No.
and really, or Amma one thing meeting in there.
All right. Well,
2000.
That's pretty weird. Anyway, so we got So in this thing, there's all right. So there's like the Zim model. There's the Rouse model. And there's no focus. Thank you. Yeah. All right. So Zim model, Rouse model, and reputation. Those are the three things we need. Zim models, basically like the isolated coil thing, and also the Einstein equation. That thing, and then for Einstein, this thing's 2.5 for spheres. And then the Rouse models is the idea that you have the bead. So you kind of use like Z and Z minus 1 and Z plus 1. And then reputation takes the Rouse model and puts it in a 2. So it's going to plug that into a 2. Right, so those are kind of the three. So this is also Zim model is also like non-draining. And Rouse model is draining. If you talk about those two, it's the hydrodynamic. The hydrodynamic effect. Like so, in other words, if you're in somewhere between the Zim model and the Rouse model, you talk about the hydrodynamic effects. So there's some kind of complicated math that has to do with how the dynamics happen. So that's more or less what I want to go through today. Like just get through this whole thing. Then the homework this week, so we have. Homework this week is like Zim model, Rouse model, and next week will be like just something on reputation, some paper. Turns out, like if you do a Google Scholar search and you look for like Rouse model, you find a few papers. And then if you look for reptation, you find like a whole pile of papers, even though they're kind of the same thing, you know. So anyway, or they're related intimately. So anyway, so that's kind of where we're going here. So first off, the Zim model, so the non-draining so the non-draining model is going to be basically the Einstein Stokes-Einstein equation, right, for diffusion coefficient. And then so an individual, if you say that the size of the particles, the Gaussian size, so R is R squared is NL squared, or R is n to the 1/2 times L, or B is L, right? Then you just end up with the diffusion coefficient will go with n to the -1 by df, where this is the size of the coil is going to go with n to the 1 by df. So you kind of just end up with that prediction for the diffusion coefficient. And then if you want to talk about the relaxation time for the system, okay, which is going to be related to the viscosity. So then you're going to go to the diffusion equation. So where R is going to be the time that it takes a coil to diffuse its own distance. So R is the size of the coil. In other words, if you're talking about the relaxation time, the Zim model, it's the time that it takes a coil to leave its own size. So the diffusion distance is its own size. That's a little strange, but that's kind of how it works. So you have this R is its own size, R squared is going to go with n, right? And then in that case, if R is its own size, then T is tau. So tau is going to be n, and then D is this -1 by df. So you'll end up with let's see. Yeah, so you use this equation, R squared is n. R squared is going to go with n. So you want to get the independence of tau. And then D is -1 by df. So if you do that, you'll end up with, how did I get that? Times tau. Let's see. Oh, I did this yesterday. It worked fine. Maybe I need to do this on paper. Maybe I need my computer. Hold on a second. Oh, look at that on this. At the same time. Okay, so we have tau D is going to be R squared, and then if R squared is NL squared, then T is tau. Whereas the time that it takes a coil to move out of itself, it's going to be the definition of tau for Zim. And then so we have NL squared here, and then D, and then tau. So we want to get the tau equals NL squared divided by D. We said that D is D is Einstein-Stokes D, so it's KT times the friction factor times NL squared, right? Which in the note says that. So if you forget about temperature, that's N times the friction factor. And the friction factor is, so it's going to be N times the viscosity 6 pi times R for Stokes law by KT. There's another L squared from that if you want it, but then R is going to be n to the 1/2. So into the 2/2 plus 1/2 gives you 3/2. Yep. That's what this thing says. Right, into the, so df is 2, or if it's a fractal dimension, it becomes 3 by df. Right, so if it's 3 by 2, but 3 by df for tau for the Zim model. Then the viscosity you get straight from this thing. So you stay, you're going to follow the intrinsic viscosity equation. So the Einstein equation, if that's 2.5, that's Einstein. And otherwise, N is the overlap concentration. So it's phi by phi star, and phi star is the mass of the coil N divided by the volume of the coil, which is R cubed, and R is N to the 1/2. So it's going to be N to the 3/2 minus 1, because that's how that works out. All right, so you get this 3 by df minus 1, which would be, if you put in 2 for the dimension, it's N to the 1/2. If it's a good solvent chain, it's N to the 0.8. All right, so even though, so this, you can see things like this is absolutely the simplest case. You'll see that it gets to be pretty confusing, like just all these scaling laws for all the, so you can see in that paper too, like the paper for this week, there's like one thing after another. If you do it a lot, you'll remember all these powers. If you don't do it much, then you'll forget about them. Then you're gonna have to go back and figure out what's going on. The cartoon picture of it is just that the coil's floating around. Now, but then you're figuring out these numbers from that. So anyway, this is the easiest of the three. So you can see even this one's not, it's kind of messy. Any questions on that thing? So that's the Zim model. That's from like circa 1940, right? And then the Rouse thing came along in the mid-50s, and then the Reptation came in the 1970s. It's kind of like there's a time sequence to these things. So let's see. So anyway, this is the melt, and the melt doesn't. So if you can measure the relaxation time in the melt, if you tag a chain, so you can take two polymers, stick them together, and then wait for the chains to like diffuse across. And then you can measure that diffusion profile. It's going to be a exponential decay curve, and the slope of that is going to be e to the t over tau. So you can get tau directly from stick two polymers together and then wait, and then get the profile of concentration across it, either with IR or with fluorescence. Right, and there's other ways to do it. You can use, people do that same experiment and they do secondary ion mass, so they blast it with ions and see where the tagged thing is. You can do it with neutron reflectivity. You can take the two things, one's deuterated, one's hydrogenous. So you can get that profile concentration with the diffusion coefficient. You can get tau from that. So you can do these measurements. This is dielectric normal mode. I don't have any idea how they did it with dielectric normal mode, but somehow they did it with a dielectric measurement. Right, so there's different ways to get it. Anyway, dielectric is going to give you the relaxation time. So they're just getting the relaxation time without any interface. They're just measuring the relaxation time for the material. But you can do it with this diffusion measurement too. Anyway, so you can get it, and you find out that tau, so if you go up to the entanglement molecular weight, tau goes crazy, like it's a steep slope, bigger than 3. And if you go into this regime where you're in the Rouse regime, it's power 2, N to the 2, which isn't, it's not the same as what we had for tau here. Tau should be 3/2, 1.5. So you can say 1.52. Basically, it's 2. Okay, so that goes for a lot of different things. Also, the viscosity is going with a power 1, and the Rouse things predict, and the viscosity goes to 1/2. So that's quite a bit different. Right. So, and then when you get to the above the entanglements, you get to reptation is 3.4. Right. So that's a lot different than 0.5, 1/2. So this is viscosity, log of viscosity, log of molecular weight. This is the relaxation time versus molecular weight. And there's the Rouse mode is here. So the Zim mode isn't here at all, right? Zim mode's like in solution. When you see in the polymer in solution, like in the paper, we're going through concentration, right? Does the, instead of time temperature superposition, this concentration temperature superposition. So when you get to solution, you kind of get to the Zim situation. And then when you get into the melt, it's like Rouse or reptation. That's kind of what you're looking at. Right, so anyway, so this there's this transition. So what's with this and squared thing? There's no model for it. So Rouse, I mentioned like last week or the week before last, which you probably don't remember, that Rouse took the model from Einstein for heat capacity. So Einstein's model for heat capacity, not Einstein, Debye's model for heat capacity. He said mass times acceleration is going to be that the atoms are separated with springs, and you can take that if one atom moves and the two neighboring atoms have some kind of effect. So the springs between the atoms, one stretches, one shrinks. And then you can model the whole thing in a 1D model and then finally turn it into 3D when you're finished. And Rouse said, oh, I mean, who knows what Rouse thought, but basically it's exactly the same model, and he never cites it. He cites something else Debye did. The paper he cites is something else Debye did, but basically he never says that this is the heat capacity model. And my impression of it is that somebody reviewed Rouse's paper and said this is exactly like Debye's paper on heat capacity, or just said it's just like Debye's paper. And then Rouse went back and looked at the Debye paper, and he found a paper where Debye did the flow of polymers. Debye also worked in polymers. And he cited that paper in his paper. And he said, oh, it's okay, I cited Debye. But the whole model is exactly stolen from Debye. So it's not exactly good enough to cite an unrelated paper. Anyway, so instead of saying mass time acceleration, which kind of gives you the heat capacity in the end, he said velocity is velocity times a friction factor gives you force. So it's like this is a force for a spring, and this is a force for a drag, right? That's the drag coefficient times the velocity gives you the drag. So you could say like acceleration, or you could say drag, or you can say both, right? So this gives you a harmonic oscillator. If you do this, if you add in the momentum part, then you get a damped harmonic oscillator or whatever. So basically these are models already existed without the z plus z plus z. That model existed for a really long time, like back to the early 1800s, the idea of like this kind of exponential decay thing. Anyway, so things build on each other, I guess. So that's how it works. So anyway, Rouse did that, and then he comes up with this solution, which is a sine wave, right? We said like e to the complex number is going to be cosine plus I sine, or sine minus I cosine type thing, right? So this function ends up being a sine wave, this e to the I times some shift factor. So that's the del parameter is a phase factor. Now you have the sine wave, and then you can shift the phase of the sine wave is going to be this del. And then the e minus t over tau, that comes from if you just say that this is just like any kind of damped oscillator. So this is the Maxwell damped oscillator circa like 1880, right? So it's like you have at that time, I guess they had dash pots, and no one knows what that is now. This is basically a shock absorber. They should just call it a shock absorber, or they call it a dash pot. So it's like a viscous element. So this is a spring element. So you hook the spring and the shock absorber together. Then you have then you do a force balance. So you have the friction factor times the velocity. So you divide it out, so you just have the velocity. Then du dx for a spring is a force, is the k spring times a position. Du dx is a force. Force times distance is energy. Du dx is force. Force is k spring times x, right? So that's the way the dumbbell is presented in physics. And if you want it to be the motion of something that acts like a dumbbell, which is what a Rouse polymer is going to be, then you have to add in like thermal motion. In other words, the thermal motion is random both in time and in well, it's basically random in time. So it's going to go plus and minus if it's 1D. So it's going to be jogging the thing up and down, right? The magnitude can also be large and small, right? But basically, the motion of the thing is going to be just some jolt, and then the relaxation, this exponential relaxation, another jolt, relaxation, jolt, relaxation. So it's always like being jolted. It's like constantly electrocuting someone, and then they recover, right? And the recovery is this
So this thing's called a memory function. Then there's other kinds of memory functions. It can be more complicated. This is the simplest one. So the simplest memory is that I want to go home. Like I'm going home to this 0 point, and it's going to take me some time to get home. That's tau, right? And like every time something moves you, the whims and of fate move you somewhere, then you always are going to go back to that 0 point by this time, relaxation time. It's a characteristic. So that's like a constitutive parameter that describes, you don't know what tau is, like constitutive parameter, like modulus viscosity. Relaxation time has no information about what the thing is. It's just like a number. It's a black box to say the response, right? So you're literally kicking it here and you're watching it kind of what the response is, right? So there's no understanding in a tau or in a viscosity or in a modulus. They're just a number to describe the behavior so you can predict where it's going to go, right? So this is like an engineering number. You're designing the system, kind of, you're using that number to do the design work. Right, so this exponential t over tau thing's been around for some time. It's not something new. So you can predict that's the behavior, and then there's this phase factor involved in this that has to do with this, because there's a separation distance between the atoms, and there's a spring constant and a friction factor that are kind of governing the whole thing. So you predict that this, you can predict that this kind of sinusoidal response is the thing you would get for Z. And then you can plug this back into that equation, and then you can get an equation that relates the 4 parameters that are in this thing. So the parameter is the position, the time, this constitutive parameter, tau, and then the phase factor, del. Or where is your atom? So basically, this is the constitutive parameter is going to be defined in terms of the phase shift factor. And they're related to each other by this equation that you get by plugging in a proposed solution into that equation and then getting, so the 2 equations, 4 unknowns, 2 equations, you get a relationship between the other 2 parameters, which are tau and del. So that's the function you get out of this thing, right? So then you have a continuous function, but you don't have what del is defined as. In order to get a definition of del, you have to say something about the system. So you need some equation that that's gonna define del, right? So the two ways to do that that people use are cyclic boundary conditions, so that you say, so you have another equation, so you have this equation that relates tau and del, and then you're going to say, well, if it's cyclic, then when I'm at L, then I'm actually L plus NR. NR is the size of a Rouse unit. How many units are in a Rouse unit? So if you plug that in, then you get an answer for what del is. So del is going to be the mode of vibration. So the things like this thing's saying that the vibrations that are happening are going to be like a guitar string. So they're going to, if you pluck the string, it's going to be vibrating, but it can vibrate, the whole string can vibrate, or half the string. So you can have a mode like here.
So both the Debye heat capacity and the Rouse model end up saying that you have a guitar string. So in the Einstein, it's a bunch of atoms, and in the Rouse, it's a bunch of Rouse speeds of NR, molecular weight, connected by springs. These are also connected by springs. So the same model. It's exactly the same thing. Like Z, ZL, ZL minus 1, ZL plus 1. It uses the same nomenclature. So it's the same thing. And then it's going to have like the primary mode, like that's the tone of the string, and there's overtones that are going to be dividing that by some number. Like, so basically 2, 3 is hard for me to draw, but if you like that, I guess, or something. Anyway, so you'll get all these overtones, and there's no limit to them. Right, so when you hear the guitar string, so the one you can kind of see, like when you hit the string, it's going to have a note like E. Right, and you hear that note, you say that's the E string, right? And all these other notes are also E, but they're E at the other octaves, like higher octaves, right? So you're gonna have I don't know, the low E, the high E, a bunch of E's. You can go on and on, up to E's that you can't hear, only dogs can hear. Right, so, or whales or something, but anyway. So anyway, most of the energy though is in this big one, right? Like the energy of this thing is all in that big one. All these other overtones are just finessing it, making it sound better, but they aren't really the main tone that you hear. Same with this, like the the lowest order vibration is the one that's going to be called, so that's going to generate one time, which is going to be called the Rouse time, that big tone, either it's an E string. And all the other fine tuning things generally just ignore them. You don't think about those at all. So you just consider that the Rouse time ends up being just one time. And then so basically you get that by doing this business of saying, well, the mode is going to be del. If I plug this into that equation, so you can see that this is squared, right? Squared del, and del goes with M, and M, the mode goes with M by NR. So the higher NR, the smaller the del, right? So del is going to be M, sine of a small number, and M by NR is a really small number because NR is a big number. Sine of a number is the number at when the number is small. So this becomes just 1 over NR squared, and this is 1 over tau, so tau goes with NR squared, which is a thing that we said somewhere here. The Rouse mode relaxation equals N squared, right? So the N squared thing comes from the solution, this thing, and you propose that solution, plug it in, you get this function. This function says that inverse 1 over tau goes with sine squared of del. And if you put in a cyclic boundary condition, then you find out that del is 1 over NR and it's squared, so tau goes with N squared. If you take the lowest order mode, which is M by NR, that would be like the first order mode of the vibrations. In other words, the whole guitar string vibrating. So it's kind of messy to end up. And the other common thing. So you say it's cyclic, so you can say the beginning and end are the same. And if you have a big enough chain, that shouldn't matter, although it does matter. And you can see simulation papers where it makes a huge difference, right? But the other thing is to say the ends of the chain have no constraint. So that means that the motion of the ends of the chain is 0, and that gives you the same answer. Basically, it's slightly different. You can see the two modes, the widely spaced and the narrowly spaced, are the I think narrow is cyclic and wide is the free end boundary condition. So you get those two solutions, the same, and then the points are the ones that you use, the del that you use for the first order mode, right? The whole guitar string vibrating, the tone that you hear. So the tone's slightly different, but basically the model, since there's a lot of oddball terms in here, then the model, it doesn't matter like which end constraint you use, really. Just gives you the same kind of characteristic features. And then so basically that ends up being that you have the relaxation time that you have, this tau, is the Rouse time, which you can calculate from this thing. And if you say what del is, you can calculate what the Rouse relaxation time is, then the thing just behaves like a dumbbell. But it's got this feature that the relaxation time goes with N squared instead of what we had for Zoom was N to the 0.5. So it's a lot different relaxation time. And then if you say, if you calculate the diffusion coefficient for it, so we had here, if you use this equation to get tau, then you end up with the D's KT over the friction factor. And then this is N, so then that gives you this N times the friction factor for tau. So we have tau as N squared, and you can get what the friction factor is. It's going to be like N for this thing. Somewhere here, whatever that is. Anyway, so you can calculate the diffusion coefficient and the friction factor for this guy the same way.
like you get that the diffusion coefficient will be go with 1/n. So before we had the diffusion coefficient goes with n over 1 by df, so it'd be 1/2 or 1/1/2, and here it's 1/1, right? So then you can get the tau squared, you can get the viscosity to the 1 for Rouse from that kind of model just by looking at it like that. So that's kind of that part of this thing. It's confusing. This is the way you see it in the paper. So he says this. So here you have G prime goes with frequency squared. So I'm going to go through where that comes from. I think I already did that, but we'll do it again. And then you get this plateau where you have entanglements and you get a plateau. And then at the end, when you're within the entanglements, so after the entanglements, so when you're within the entanglements of small size, and you can see this frequency of the 1/2 dependence of both the storage and the loss modulus of the same dependence of frequency. So in that region, that's called the Rouse region in the frequency space. So there's different ways to look at this. There's like a molecular weight way, right? We have like the Rouse is at this low molecular weight end. And then there's the concentration way, like you're saying, like Zim, and then it's going to go to Rouse. And then it's going to go to entanglement. It's like reptation and concentration. It's go like Zim, Rouse, reptation. And then here you're saying like molecular weight, you're saying Rouse, reptation. And if you go in frequency, the problem is like they're in different order, right? Like so here, down here you have at low frequencies, this is a really long time, you have viscous flow. So this is just liquid flow like Newtonian flow. And then you get to the entanglements, it acts like a rubber. And then once you get to higher frequency, it flows again, but by Rouse, it's a Rouse flow. So this is viscous flow, that's Rouse flow. And Rouse flow, the signature is this frequency to the 1/2. So not only is it confusing just to look at it, but then even when they put it into plots, like with different plots and the order of the things are different. And so the whole thing is like a mess, right? In other words, you can see that if you want to do rheology, you're going to have to really get serious about it. Messing around with it a little bit isn't enough because it's too complicated. Even just getting the basic ideas about it is like pretty complicated. So anyway. All right, so some of the rules, these are two rules that you hear tossed around. So the first one is in the paper, and it's in the Norm Wagner paper too, like the Cox-Mertz rule. You can say if you put a so this is based on the idea that there's a single response function. So this exponential t over tau minus t over tau is a response function. And if you know the response function, however complicated it is for material, then you can predict all the properties of it, static and dynamic. In other words, or continuous or dynamic or oscillatory. Right? In other words, if I put it into a cup and bob viscometer and spin it, then I get the viscosity. If I spin it faster, the viscosity drops if it's shear thinning or something, right? So anyway, so that same response is going to be seen if I do an oscillatory measurement and do different frequencies. Because there's only one response function, and I can also predict the compliance. In other words, if I put a weight on it and how does the gum drop, or if I do a modulus like pull on it. So all those different things, if the material has a single response function, I can predict all of them from the same thing. And if it has a single response function, I can predict the loss and the storage. Whereas I can predict the viscosity and the modulus from the same function. Right. So that's kind of linear response theory. I guess that's the basis of it, which was originated in dielectric response in the 1950s when they were doing radar and things. Right. So this idea that you have that a material, you have to look at the different kinds of responses that a material has. I mean, in terms of say mechanical or electric, right? But even electric and mechanical are linked because you can do the same, like say glass transition, they both involve molecular motion. So there still is a molecular response function that is responsible for both phenomena. Right. So basically there's a lot to this. Like it's like a can of worms and you open it up, it's like, oh, that's interesting. And then like you keep digging, it like keeps going down. You find out that the entire universe is just this response function, and then like you can kind of build back up from there. Not necessary to live your life, but basically you could do it. Anyway, Cox-Mertz rule is one of the things you find out along that path, right? Is that frequency and time, if you do the frequency measurement, do the time measurement, you can relate those two together, right? They're the same thing. So that they have the same response function, they're the same thing, right? So it's called the Cox-Mertz rule, and people talk about it in rheology. And it's in that Wagner paper. And he mentions it in our paper too this week. So that's one of the things. The other thing that you'll see is called this Kramer's-Kronig relationship that says if there's a single response function, this mu of t, then the loss and storage are both related to that through this function. Like in other words, the integral of the response function over all time, from the beginning of time to the end of time, times cosine will give you the storage. And then the integral from the beginning to end of time of the response function times sine will give you the loss. There's just one response function for both the loss and the storage, even though the two things seem to be quite different. One involves dissipation of heat, and the other one's kind of storage of energy. Right. So it's saying that the storage of energy and the dissipation of heat are the same thing. It's just this response function, which is exponential minus t over tau thing, right? Or could be, in the simplest case, that's what it is, right? Simple exponential decay. It's also called a Debye relaxer. So anyway, and everything Debye did was some exponential. You remember that. So if he says Debye, it's like exponential, just write exponential of whatever. And it's not a Gaussian, so it's got to be just exponential of the thing. Like the Debye length is going to be an exponential function of whatever charge and charge concentration. Anyway, so if that's true, then it's possible to go backwards from the A prime to go to A double prime, which could be G, could be the modulus, shear modulus G, storage modulus, and loss modulus. It could be the compliance, or it could be the viscosity, so storage and loss viscosity, where the loss viscosity is the modulus, the storage modulus, and the loss viscosity, the storage modulus, the storage viscosity is the loss modulus. Like they're related that way. So anyway, so all these things can be related to each other, and there's equations that relate everything together, right? So this Kramer's-Kronig relation is how you get them, so it's basically going to be an integral of some of your zero frequency. To get the storage and the loss, you integrate from minus infinity to infinity of the storage of the loss. And to do that, you have to have a zero frequency. And the problem is, like, if you scan this through frequency, you're going to at some point reach frequency zero. Then this thing becomes infinity and it blows it apart. So you need to use this Cauchy integral P to do it, which says, I'm not sure I wrote it here. Oh, this is the Cauchy integral. The Cauchy integral is going to be you can break that into two parts. And limit is theta goes to zero, where you have the zero, you go up to zero, almost to omega zero, and you go almost to omega zero. So you skip where it goes to infinity. Just cheat. You kind of cheat. You need to do this integral minus infinity to infinity, and you cheat. You say, like, well, I'm going to come really close to infinity, but I'm not going there, because these two things will offset each other. So basically that's called the Cauchy integral, which is like a cheat to solve this problem. So you'll see that term also, like use the Cauchy integral to solve the Kramer's-Kronig relationship. That's in a lot of papers, like you'll see that. And I'm not sure that I explained it very clearly, but that's the idea here. You want to be able to calculate the loss from the storage from the loss. You need to use this Cauchy integral. Kind of a cheat function. So you can see, like, if you have the loss, you can get the storage. If you have the storage, you can get the loss. And you do this P, which is Cauchy integral, which means you're cheating. And you get to or omega 0, or omega equals omega 0. Anyway, so that's two things. That's not answering this problem, but that's two things. This is just the, so this, he tells them Maxwell model, simple relaxer, dumbbell model, they're all the same thing. You end up with this exponential T over tau, right? That's the idea. So the simplest way to do this is to say, say that do the compliance. So you say compliance is the opposite of what you're used to, right? So you're used to like modulus and strain is a stress like that. That's tensile stress. So it would be like 1, 1, 1, 1, 1, 1. Or X, 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 X. If you're going, not chromosomes, but you're going like pulling it in the same direction, X, if the length is changing. And we said like, because of the incompressibility, that measurement, that tensile measurement is useless in Polymer, so you shouldn't do it if you can avoid it. And the best experiment to do is something where you're doing a shear measurement. So like this, you put your stuff in here, and you're going to do an oscillatory shear. And then it's going to be usually called tau, so it'd be like tau 1, 2, or XY, and then it's going to be the shear modulus 1, 2, XY, and then the shear strain, which is 1, 2 also. So they're tensors, right? So basically, this is the one we want to use because this has no dilatometric stress. You're not changing the volume, and you're using this because you have a constant rotation frequency, but as you go out, so the speed gets higher as you go out, linearly higher as you go out on the cone, and then the gap also gets linearly higher. So if you do the change in length, which is like the speed times time, and then you divide by the gap, and that's your strain. Well, they both depend on R, right? They're both like R. The velocity is proportional to R, and the gap is proportional to R. Those cancel. You get a constant strain as you go across the gap. So you need to use a cone and plate. If you use just two plates, it doesn't work that well. Although people will use plate. The angle, so it doesn't matter what angle that plate is. So typically it's like a degree, like something you can't see. The angle, yeah, the angle of the cone to the plate is like something like a degree, maybe less than that. So basically, it doesn't matter what angle it is. It can be any angle. So use the smallest possible angle, which is basically the smallest would be two plates. So sometimes they use two plates if this stuff is some reason to do that. Anyway, so we got so we're looking at shear modulus, and then topic oscillatory strain. Oh yeah. Then what do we then you want to know the, so this is when you apply a fixed strain, right? So strain 0, and then you get the stress response in time. So I'm going to take the stuff, and I'm going to strain it. So I'm going to go like that. And I'm going to measure the force as a function of time. Right, so I'm going to do it like a delta time for this, meaning it's a step function. I'm going to look at the step function like that. And then the tau, I'm going to look at it over time, relax. The other thing you can do is to look at the strain as a function of time, and then look at the compliance, and then put a 0 stress on it. So that's where you take your gum, and you put your weight on it, and then over time the gum just moves out, right? That both of these are going to have like an e to the minus t over tau behavior, right? They're both going to follow that same ut, this response function. Right. So anyway, that's the gist of it. It turns out like the it's easier to work with compliance than it is to work with modulus on the beginning, right? So also all the math that was originally done was done on compliance because they did it with dielectrics. So with dielectrics, it's easier to apply the fixed electric field and then watch the dielectric polarization decay than it is to put a fixed polarization and watch the field decay. Or you can't do it. You can only measure compliance with dielectric, can't measure modulus. So hence all the math is done with compliance first, right? And you can get the same tau from both dielectric and mechanical. So you can get things like the glass transition temperature, you can get it with either technique, so and this is much easier, like there's no grip slip. You can have an arc across the sample if you put a high enough field on it, but basically you'll know when that happens because you'll smell burning, but with mechanical, you can do the measurement and you could have grip slip or the thing could neck. Stuff happens in mechanical a lot more easily. Yeah, and the dielectric you can do on your desk. You don't need an instrument. You can do it, basically you could have a pocket held dielectric measurement. It's like could be really small. It's just put a field, measure the polarization with a voltmeter. Anyway, so we got this compliance, complex compliance is going to be the same function that we saw before. So we had del here before, but so there's basically going to be a phase behavior. This is frequency, and then you have this is the mu t, the response, right? So it's the Fourier transform. This is a Fourier transform when you change it from time of your relaxed function to frequency. You end up with the complex frequency. So when you do that, if you multiply two exponentials, you sum, so you end up with this sum, right? And if you do an integral of an exponential, it's an exponential, right? Integral of e to the x is e to the x dx. Integral of e to the x dx is e to the x, right? So the problem is that dt isn't the derivative of time times this thing, so you have to divide by this thing, 1 over tau plus 1 over I omega. Right, so you divide by that, and then you do have dEx dx, and the delta j pops out front, right? So then you do the integral. Well, when it's 0, e to the 0 is 1, and when it's infinity, e to the minus infinity is 0, because it decays to 0. Right, so this one goes to 0, that one goes to 1. So you have 1 times delta j over 1 over tau plus whatever, and there was a negative here, so it's -1, so that gets rid of the negative problem here. This would be 0 minus that thing, but it's negative, so it ends up being positive. So you get this simple function for that, relatively simple. Then if you multiply, so you want the complex part in the numerator, not the denominator, so you can have your j prime, j double prime, because the j prime has no imaginary and the j double prime has imaginary. So you want to get rid of that in the denominator, put it in the numerator. So you multiply by the complex conjugate over tau minus I omega. And then that clears the bottom out, because that'll be 1 over tau squared. And then this is minus, then I squared is -1, so that's omega squared. And then you have minus and plus, those go to 0. So you just have omega squared over tau squared. And then for the numerator, you have delta j, and the other one's going to be omega delta j. Right. So you have only if you go to low frequency, so you want to say, well, flow. So viscous flow is at really high time, a really low frequency, so that when you're oscillating like ooh, very slowly, then you get viscous flow. If you go fast, it becomes solid. All right, so that means that at low frequency, 1 is much bigger than tau omega, because you're way below the relaxation time. That's why it flows. If you're at the relaxation time, it doesn't flow. So basically, you're way below that. So that term goes to 0. You have a constant compliance. That thing doesn't have a frequency dependence. That's like J0. Then the frequency, that term goes to 0. You just have that it's proportional to frequency. So the loss part is proportional to frequency. This one's just fixed. Right, that one's just your J prime, whatever, J0. Right, so compliance just has this flow term here. This second term, the imaginary term, is just basically the flow. In fact, this is going to be 1 over the viscosity. The compliance is going to be frequency divided by viscosity. So anyway, that's, if you want to look at it this way, so that function, see, this is like becomes a basis of what the Maxwell model looks like. Like what does a single relaxer look like in mechanical? So you're going to have, if you take log of this thing, so you take 1 over omega, and this becomes omega. Like if you divide by omega, that one becomes just delta J. Then this one becomes 1 over omega, that becomes omega. Take log of those, put on a log scale, then it's 10 to the minus log, 10 to the plus log. So when that thing goes through tau at 1, so omega tau 1, it's got a peak, and then it decays on either end, because at the low end, this thing becomes very large, and 1 over something large is small. At the high end, this thing becomes very large, 1 over large thing small. So it decays on both sides and gives you this kind of bell-shaped curve that isn't Gaussian. It's this function. And then the other guy, as you go to low frequency, it goes to tau dot J. So that's our flow, that's our modulus in the flow regime. And then at the high frequency, this thing just gets smaller and smaller. Almost, basically, that's called a Lorentzian decay. Right? It's this 1 over something squared. That's Lorentzian. So it's the Lorentzian decay function. Right. So that's basically what we're looking for when he says in the paper, like Maxwell model, that's what it is. Okay. So, but this is compliance, and he's talking about shear modulus. So how does that work? Because this has to be completely different, right? Absolutely completely different, because you have that the complex modulus has to be 1 over the complex compliance. That's the definition of it. And this has got to lead to a mess, right? It's got to lead to a nightmare. But it turns out it leads to exactly the same function, right? Because if you substitute in other terms, so you have to do this inverse thing and then mess around with it, and then substitute in this relaxation compliance, and then this tau hat instead of the tau, which is related to the relaxed compliance and the unrelaxed compliance. And then you define a relaxed modulus and unrelaxed modulus. Then you get a change in modulus, unrelaxed minus relaxed. If you do all those substitutions, and you'll get the same function. Like essentially it's the same function, just the terms are defined in terms of each other. And meaning if you have the same function, it's going to have the same, like this same behavior. So the Maxwell behavior is going to be the same for the compliance and for the modulus. So if you see that kind of behavior for your storage and loss, which is the normal behavior, in other words, you'll say that this is like the glass transition temperature. So peak in the storage modulus or in the loss modulus. And also you can define glass transition as the point where inflection point in the decay of the storage modulus, right? So that's kind of where tau, we would reach tau for the system, right? So anyway, so that works for both the storage and the loss, because you can mathematically switch from one to the other, right? So it's kind of messy, but there it is. The other thing you'll see is this, like the Cole plot. Okay, so it turns out, and this is originated in dielectrics, but went to mechanical too. So you say, and this is the kind of the way that you define that you have a Debye relaxer, a single relaxation time for your system. Like in other words, it's a simple system. So what are the options? Like your system could be more complicated than that. It could have multiple relaxations, or your like your 0 point of relaxation might be. So if you have, say, in the Strobel's book, he has a case of cites a paper where he has a molecule that has a simple relaxation. Then he tags a molecule onto the side of a polymer and goes through the dielectric response to that same thing and says, like, well, it has a simple relaxation, but it shifts this relaxation point, the tau 0 point over. So Cole, you plot the loss versus the storage, right? And you expect to see a semicircle, because if you can rework this equation, you can rework it. This is the storage and the loss. You can rework it into the equation for a circle, like x minus a squared plus y minus b squared is r squared. The radius of this circle is going to be r squared. That's going to be delta j squared over 4, or delta g squared over 4 if it's a modulus. And then the a and b parts are like these things, like that and that. So b, so the loss part should be centered on 0. So the circle, the semicircle should be centered at 0 because there's no minus B, right? And then the storage part, in other words, how far it's shifted from 0 on the x-axis should be this delta J, blah, 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 right? So basically each point on this is at a different frequency. The high frequencies are over here because they're at high storage modulus, which is where it's, in other words, when it's low storage modulus, the storage modulus is at low frequency. The high frequency is high storage modulus. So basically, a circle means you have a single relaxation time. This is high frequency. High frequency, you see perturbations when the system has like constraints on it. So if it's got network or something at high frequency, you start to see these constraints on it. Then you'll see deviations in the Cole plot over here. Otherwise, it's kind of a mystery. Like you can get some numbers out of it, but the people will show Cole plot. They want to just say there's a single relaxation time. The system's well behaved. That's kind of what they're trying to say. And you can get some numbers from the plot. And if it shifts around, this guy shifts left and right, then you can say something about why that happens. Like you have certain constraints. So that means your loss, that means this number isn't, or that means this number is shifting around. So if it isn't centered up and down, that means there's something going on with the loss. Anyway, people make stories up about it. There's things you can do with it, you know. So anyway, so that we're out of time, but anyway, hopefully that helps a little bit. That's kind of half this stuff. So I'll go through this. Let's see. So Wednesday, so the homework's due, right? Tomorrow.
Yeah.
Yeah. So if you have any questions on it or anything, no one's looked at it probably, great. So you're just gonna do it now. So just email me with your questions about it. It's kind of this same stuff. It's partly this stuff, you know, so hopefully that'll help. If not, then just email me and I can try to solve it, you know.
Yeah. During the sharing is taking place, the plate, and then we call that angle in between contact angle.
No, contact angles for when you have liquid on a plate, and you say you put a drop of oil on a plate, then it's got an angle like that, right? Because it doesn't like the plate, so it tries to make a circle. And if you put water on a plate, it's like that or like that, depending on if the plate's hydrophilic or hydrophobic. That's contact angle. From that, you get the surface tension. Yeah, so this isn't the contact angle. I can see why you get confused. Basically, they're completely, absolutely different. Like if you put a straw into a liquid and the straw makes a meniscus, that angle with the straw is the contact angle, right? And if you put it into oil, it will go up, and the water will go down. You know, so that's because the surface tension of oil and straw and water and straw are quite different, right? So you can measure from that angle, you can measure the surface energy. Yeah, but it's not it's not this thing.
Thank you.
Right. Good question. I mean, it's like there's a lot of angles. You know, so.